Okay, we'll go ahead and get started. I wanted to today go back. I forgot to go over lesson 19 with y'all. So I wanted to go back and do that with you guys today. And lesson 19 is on something called applied optimization, and it involves derivatives. And let's start by figuring out what applied optimization really means. Let's say you're trying to find the dimensions of a rectangle with a fixed perimeter having maximum area, or you want to find the dimensions for the least expensive cylindrical can of a given volume, or you want to find out how many items should be produced for the most profitable production run. If you noticed, the key words were like most or maximum or least or sometimes smallest. Those key words deal with derivatives and specifically max or min values. So we will likely have to use the first derivative test to find some of this similar information. Each of these questions asks for the best or optimal value of a given function. In this lesson, we'll use derivatives to solve a variety of optimization problems, mainly in mathematics and also geometry. So let's start with the very first question. And let me screenshot it and put it on our whiteboard. And give me 1 second. Let me share the paint tool. All right. Find the smallest perimeter and the dimensions for a rectangle with an area of 121 square inches. Two things are mentioned here about the rectangle: the perimeter and area. So that means we need both formulas. So we have area equal to length times width. And the other formula we'll be using is P equal to 2 times the length plus 2 times the width. Now, eventually, we're going to take the first derivative, but in order to take the derivative, we must have all the letters to be the same. So I'm going to use the area formula to kind of get the letters to be the same. So in place of A, plug in 121 equal to L times W. And it does not matter which letter you get by itself. Excuse me. I'm going to solve for W by dividing both sides by L. So W is the same thing as 121 over L. What we do with this fraction is, in place of the W in our perimeter formula, plug in that 121 over L. So we have 2L plus 2. Because we need to take the derivative, first derivative, to make it easier on ourselves, let's change the 121 over L into a negative exponent. So that will be 121 L to the negative 1 power. which is 2L plus 242 L to the negative 1 power. Now we're ready to take the first derivative of this. The derivative of 2L is just 2. We use the power rule to find the derivative of our second term. So we'll move the exponent to the front and multiply it by the 242. So that gives us negative 242. And remember with the power rule, to finish it, you subtract 1 from the original exponent. So that would give us L to the negative 2 power. Now let's rewrite that back with a positive exponent, that last derivative we found. So that would be negative 242 all over L squared. Now we need to remember with the first derivative test and also the second one, with the first derivative test, we have to find any critical values. So to do that, we set our first derivative equal to 0 and solve for L. Well, what I'm going to do is move this fraction to the left-hand side by adding it to both sides. So that gives us 242 over L squared equal to 2. Now that 2 is understood to be over 1, so we can cross multiply. We got 2L squared equal to 242. Now we're almost done finding L, but we need to first of all divide both sides by 2. And that gives us L squared equal to 121. To get L by itself, you do the opposite of squaring something, which is taking the square root of both sides. Now, normally when you take the square root of a number, you have two answers, but we reject the negative answer because we can't have negative length. So our length is exactly 11 inches. Now we need to find the width. So we'll go over here and replace L with our 11. So the width is also 11 inches. Now the last thing we need to find is the actual perimeter. And you can plug in your length and your width back into the perimeter formula. So that would be 2 times 11 plus 2 times 11. And when you figure this out, you get 44 inches for the smallest perimeter. Before we look at our next problem, any questions off campus or on campus with this example? All right, let's look at another problem from lesson 19. And let me screenshot it and paste it to our paint whiteboard. All right, next question. A rectangular plot of farmland will be bounded on one side by a river and on the other three sides by a single strand electric fence. With 2,800 meters of wire at your disposal, what is the largest area you can enclose and what are its dimensions? Draw a picture, it helps you get everything together. So we have plot of farmland bounded on one side by a river and the other three sides by a single strand fence. Now we can label the width as X and the length as Y. And the 2,800 meters of wire is actually the given perimeter. Now we'll be using the area formula for a rectangle again. A is equal to length times width, or X times Y. But we won't use the traditional perimeter formula for a rectangle. We do not count the side bounded by the river. That's taken care of. So we just add all the other sides together, just a single strand electric fence that goes around. So we have X plus X, or 2X, plus Y. Now, eventually we'll need to take the first derivative, but in order to do that, we need the same letter throughout. So let's use the perimeter formula and get one of our letters by itself. It doesn't matter which letter, but probably since Y is got a 1 in front of it, let's get Y by itself. So subtract 2X from both sides. And we have Y by itself equal to 2,800 minus 2X. Now we're ready to substitute for the Y in our area formula. So replace that Y with the 2,800 minus 2X. So let's distribute the X. And that would be 2,800X minus 2X squared. Now we are ready to take the first derivative. So the first derivative of negative 2x squared, I'm just rearranging the terms so they'll be in decreasing order. The first derivative of negative 2x squared is negative 4x. And the first derivative of 2,800x is 2,800. Now, part of the first derivative test is to find any critical values. So you set your first derivative equal to 0 and solve for x. Now, I'll go ahead and tell you when you solve for x, you'll get 700 meters. So 700 meters represents the width. Now we need to go back and find the length. Use this equation right here, since we got y by itself already. And in place of x, we'll plug in the 700. Now, when you perform the calculations, you get 1,400 meters for the length. Oh, the last thing we need to find, excuse me, the last thing we need to find is the largest area. So just multiply 1,400 by 700. So the largest area we can enclose is, let's see, 980,000 square meters is the largest area we can enclose. Are there any questions about this optimization problem? All right, let's look at another geometry problem. That involves a triangle. Two sides of a triangle are 6 and 11. Find the size of the angle theta in radians formed by the sides that will maximize the area of the triangle. This is not a right triangle. It could be any type of triangle, and it's not drawn to scale. So we have our two sides here, 6 and 11, and we got the angle theta in between them. The problem mentions area of the triangle, but we cannot use the traditional area formula for a triangle because we're not given a height. There is another area formula that you can use that involves a trig function. And that is A is equal to 1/2 A times B times sine of C. And I forgot, let me label our triangle here. Oops, sorry about that. Let me paste that letter. It's labeled backwards, but honestly, it does not matter. C is our given angle, and the side opposite angle A is your side A, and the side opposite angle B is side B or 11. Now we're going to plug everything in first before we take the first derivative. So we have 1/2 times 6 times 11 sine of theta. Now, half of 6 is 3, and 3 times 11 is 33 sine theta. Now, we need to take the derivative. So the derivative of sine 33 sine theta is 33 cosine theta. Although there's a trig function present, we still need to find any critical values by setting our first derivative equal to 0. Now let's get rid of that 33 by dividing both sides of our derivative by it. So we have 0 equal to cosine theta. Now we need to figure out on the unit circle, where on the unit circle is our angle or cosine theta 0? Or we're trying to figure out the particular angle measurement. What I'm going to do is pull up a unit circle. And let me see if I can find a clear one. Okay, this one is a little colorful, but it'll do the job. We need to find the angle measurement where cosine is 0. Remember on your unit circle that cosine is the x value or x coordinate. So where cosine is 0 happens at 90 degrees or pi over 2. And also down here at 270 degrees or 3 pi over 2. So those are our two answers for theta. So theta would have to be pi over 2 and 3 pi over 2 in order to maximize the area of the triangle. Again, the reason why I use this specific formula is because we are not given a right triangle. We're not given a triangle with a height. We're just given a triangle with two sides. So that's why we couldn't use the traditional area formula. We had to use a trigonometric version. Are there any questions here on campus about this problem? Okay, the last time we met, we talked about antiderivatives. So I want to just review that because, as I told you last time we met, antiderivatives are the same thing as taking an integral or integrating. And Calculus 1, no matter where you go to college or university or institution, Calculus 1 is usually split into two halves. The first half of the term is derivatives, and the second half of the term is all things integrals. So that's why I want to go back and review how to find an antiderivative. Let me pull up the power rule for derivatives. Here we go. And the power rule for derivatives, this is a rule that we've been using a lot of the first half of this semester. So we're used to it. Power rule, you guys know, is you move the original exponent represented by n here to the front and multiply it by any constant that may be there. And then to complete the power rule for derivatives, you subtract 1 from the original exponent. With an antiderivative, you are doing the opposite or going backwards. So instead of subtracting 1 from the original exponent, you are actually going to do the opposite and add 1 to it. Instead of multiplying your exponent by some constant that's there, you're going to do the opposite of multiplication, which is division. So we'll divide our antiderivative by our new exponent, n plus 1. Now, to take into account any possible constant we may have, for an indefinite integral or antiderivative, you always put a plus c to represent any possible constant. And let me explain why we use plus c instead of just an exact number. For example, if you had these series of functions, x squared minus 11, x squared plus 9, x squared minus 3, and x squared plus 17. Well, no matter what the constant is, your first derivative for all 4 of these is 2x. So that's why when we are actually finding the antiderivative, or going back and finding the original function, we have to put a plus c to ensure if there's some type of constant there. Let's use our antiderivative formula to find some antiderivatives. All right, first example, we have, let's see, x squared plus 3, and we need to find the antiderivative. Antiderivative means you're taking the power rule and doing it in reverse. So for our first term here, you add 1 to the original exponent, and instead of multiplying, you're actually dividing by your new exponent. So that would be x cubed over 3 for the first part of our antiderivative. Now, to find the antiderivative of a constant, you can rewrite the constant in terms of the given letter. So 3, we can rewrite that as 3x to the 0 power. Because x to the 0 power we know is 1. Undo the power rule with this term also by adding 1 to the original exponent, And following our rule here in red, we divide our antiderivative by our new exponent, 0 plus 1. So that's going to be 3x to the first power, or just 3x, all over 1. And that is just 3x. And anytime you're taking the antiderivative, put a plus c to represent any possible constant. To check your answer for an antiderivative, this is actually the original function we found. So to check your answer, just take the first derivative of it. Let's look at another example in which we are given a derivative and we're going back and finding the antiderivative or the original function. So next example, we have 2 over x to the 5th power minus 7 x to the 6th power. Before we find the antiderivative, it's a good idea to rewrite that first term as a negative exponent. So that will actually be 2x to the negative 5th power. Now let's use our rule over here to the right and undo everything. So we'll add 1 to the original exponent for both terms. And according to our antiderivative rule, we'll divide each term by our new power, our new exponent. So first we'll divide by negative 5 plus 1. And the second one we'll divide by 6 plus 1. So when we simplify, first part we got 2x to the negative 4th power all over negative 4 minus 7x to the 7th power all over 7. Now, a few things we can do with the first part of our antiderivative. We can cancel out or simplify 2 over negative 4. And we can also rewrite the x to the negative 4th power with a positive exponent. So that will become now negative 1 over 2 x to the 4th power. Now for the second part of our answer, the 7's cancel, leaving us with just negative x to the 7th power over 7. Oh, I'm sorry, that's not right. Undo that. It would just be negative x to the 7th power by itself. And don't forget your plus c to represent any possible constant. Are there any questions so far on finding an antiderivative? All right, let's look at this next problem. And I will leave our antiderivative formula up here for us. And we will look at the next example. All right, next example, we need to find the antiderivative of square root of x. First thing to do is rewrite our radical where it contains a rational exponent. So square root of x is the same thing as x to the 1/2 power. Now we can use our antiderivative formula. We'll add 1 to the original exponent, and we'll divide by our new exponent, 1/2 plus 1. Well, 1/2 plus 1 is 3/2. So we have x to the 3/2 power all over 3/2. Since we're dividing by a fraction, that 3/2 is going to flip to make it now 2/3 x to the 3/2. I don't mind if you leave your answer in rational exponent form. You don't have to change it back to a radical. However, if my math lab marks this answer or this similar type of answer wrong, please let me know. Oh, and the last thing, don't forget when you're taking an antiderivative, put a plus c to ensure any possible constant is represented. All right, just like with derivatives, there are antiderivatives or integral rules for trig functions. So let me share these with you guys. Integral rules for trig functions. And let me find the table with the basics. Hold on just a minute. Try this. PDF. Okay. Don't think this is what I was looking for. Hold on. Common derivatives and integrals. This may be what we're looking for. Okay, this will work. I'm just going to, for now, because for now, all you need to know are the first 6. So let me copy and paste them and go over each one. All right, these are the trig functions, the integral or antiderivative of each one. Cosine is antiderivative is sine plus some constant c. The integral or antiderivative of sine is a negative cosine plus constant c. The integral or antiderivative of secant squared is actually tangent plus a constant. Excuse me. The integral of secant tangent is just secant plus a constant. And I should say these are all indefinite integrals. Indefinite integrals are the only integrals that have a plus c. Next, the integral of cosecant cotangent is negative cosecant plus a constant c. And then finally, the integral or antiderivative of cosecant squared is negative cotangent plus your constant c. So make sure that you know these six basic antiderivatives for lesson 19 and beyond.